Okay, so we are going to take a look at example 1 on page 65 of your workbook here. Okay, and this is our first example of using the derivatives of a function to figure out information about how the graph of the function looks. Okay, and this is kind of a long example the first time that you see it, with a lot of new ideas. So I'm going to break this up into two separate videos. We will do just parts A and B of this example in this particular video. Okay, so the first part of this asks us to figure out where f of x is increasing and decreasing. You might remember that where a function increases or decreases has something to do with the first derivative of the function, where it's positive and where it's negative. Okay, that's the strategy that we're going to use to answer this question. And so we're going to start by seeing if we can figure out where the derivative is 0. All right, so let's calculate the derivative together. Just using the power rule, we're going to get 4x cubed plus 12x squared, and we're going to set that equal to 0. Okay, which gives us an equation that we need to solve. Notice that we can factor a 4x squared out. Okay, so we'll do that. And if you take the two pieces, the two factors, and set those equal to 0 individually, we get either 4x squared equals 0 or x plus 3 equals 0. And that leads us to two solutions, either x equals 0 for the first piece or x equals negative 3. These are the places, again, where the derivative is 0, and we had a name for points like that. They were called critical points. And what we're going to do now is to use those critical points to make what's known as a first derivative sign chart for our function. Okay, so think of drawing a number line, and I'm going to mark that number line with these two critical points that we found, negative 3 and 0. And I'm going to label this with f prime of x, since that's the derivative that we're interested in. That negative 3 and 0 that we found, think of those numbers as splitting the number line into three zones. There's this zone here for numbers that are less than negative 3. There's a zone in the middle for numbers between negative 3 and 0. And then there's a zone to the right, numbers that are greater than 0. We are interested in knowing whether the derivative is positive or negative in each of those three zones. Okay, so to answer that question, we are going to pick what's known as some test values for our function, starting with the zone on the very left-hand side. So what would a nice number be that's a little bit less than negative 3? Well, one possibility is just negative 4. That's a test value in our leftmost zone. And we're interested in knowing, is the derivative positive or negative at that number negative 4? Well, let's go over here to the left and figure that out. So we're going to take that negative 4, just plug it into the derivative. Okay, and I'm going to use the factored form of the derivative, 4x squared times x plus 3 that we calculated, and just plug that negative 4 in. Okay, and what we're really interested in here is, do we get a positive or do we get a negative number? Well, let's see what happens here. We're going to get 4 times negative 4 squared is 16, and the negative 4 plus 3 is negative 1. And if you multiply those three numbers together, 4 times 16 times negative 1, you're going to get negative 64, which is less than 0. Okay, which tells us that our derivative is negative in this first zone of our chart. Okay, so I'm just going to put a minus sign there. Okay, and now we're going to do the same thing in the other two zones of our chart. So between negative 3 and 0, we'll pick a nice number. How about negative 1? That's between negative 3 and 0. And we'll go over to the left and plug that into our derivative. Okay, same calculation as above, just a different number. And if you go through all of the arithmetic there, 4 times negative 1 squared times negative 1 plus 3, this time you get a positive number. okay, which means that we're going to have a positive in our sign chart between -3 and 0. Okay, and then finally, we need one more test value, a number that's a little bit bigger than 0. How about 1? Okay, and we'll plug that into our derivative. And this time, if we do the arithmetic, 4 times 1 times 1 plus 3, everything is positive, and so we're still going to get a positive number. Okay, so we have completed our first derivative sign chart. Okay, and the question is, what does all of this mean? Okay, well, let's switch colors here again. So remember, for example, that the two plus signs that you see in the chart are telling us that the first derivative is positive in those two regions. Okay, and a positive first derivative, again, means that our function is increasing. Okay, so here's what we could say. We could say that f is increasing in the two locations where we have a plus sign in our chart, which would mean that we're increasing between -3 and 0. And again, everywhere to the right of 0, from x equals 0 to x equals infinity. Those are just the two intervals where we're getting plus signs in our sign chart. Okay, and similarly, over here in the leftmost zone, where we've got a minus sign, that's where f is going to be decreasing. Okay, and so I'm going to circle that because that is our answer to part A. Okay, maybe just a brief reminder about notation here. When you see something like -infinity to -3, remember that that's representing an interval of numbers. So we could have also written that as x values between -infinity and -3. Just a different way of writing it. Okay. So let's talk for a minute then about part B in this problem. Okay, what's nice is we can use the same sign chart that we made in part A to answer this question as to where we have local maximum and local minimum values. Okay, let's see how. Okay, so I'm going to look back up here at the sign chart, okay, that we constructed. And remember, for example, that the minus sign that you see over here to the left, and the plus sign that you see over here to the right is an indication of where the function is increasing or decreasing. So I can look at this -3 and the signs and see that my function is decreasing to the left of -3 and increasing to the right of -3. Okay, so this little graph that I drew here is kind of what f looks like. And notice that right at -3, we kind of reach a valley. And that valley is a local minimum. Okay, so going down to part B here, we have just discovered that our function actually has a local minimum at x equals -3. Okay, I'm going to leave a blank here because we're going to try to figure out what that value is in a minute. Okay, do we have any local maximums? Okay, well, if we look back up at the sign chart from part A, it doesn't look like it, because to have a local maximum, we would need to go our graph to go from increasing to decreasing, which would mean we would need to have a plus sign on the left and a negative sign on the right, and we just don't see that in this chart that we're looking at up here. Okay, so there's only one local minimum, and it occurs at this number -3 up here in part A. Okay, whoops, and I just made it disappear. Sorry about that. Okay, so we want to complete part B, there's actually one more step. Okay, we've convinced ourselves graphically that there's a local minimum at -3, but what is its output value? What would the y value at -3 be? Okay, well, we can figure that out by just going back to the formula for our original function. And if I can just scroll up for a second here. Okay, the formula for our function looked like x to the fourth plus 4x cubed minus 10. We're going to take the negative 3 and plug it into that formula. Okay, so just to be consistent with colors here, we're going to take negative 3 and just plug it into that formula for the original function. Okay, and you can double check my arithmetic there. Okay, that's maybe a job for your calculator, and out will come negative 37. Okay, that would be the y value of that point where our graph has a local minimum. Okay, and that completes part A and B of